On to moderation. People get these confused. If you think of mediation as like the third wheel analysis, that'll help you keep it straight. Because moderation is interactions. So using an interaction effect, which is very similar to ANOVA. So we're going to make a lot of ANOVA references right now. I think you guys have all like brain farted ANOVA out, but this is how you would do ANOVAs in regression. All right, so do violent video games make people antisocial? This is from the field book. So we're going to use aggression as our DV. Our IVs are going to be callous, unemotional traits. And then the number of hours spent playing video games. I know several of us are big video game people. I don't know if I would consider Legos violent, but we can pretend, right? And their interaction. So when you're doing power for these, it's 3 predictors. And maybe sometimes even more, okay, if you use categorical variables. But minimally, it's at least 3. When people draw these types of models, they tend to use this just straight arrow thing. I wish they wouldn't even draw this, because then that's, I think, what's conflating mediation moderation, because you got the triangle diagram, and this is essentially the triangle without the extra triangle lines. And I don't think this picture really helps explain what's going on, but if you see somebody reporting a picture like this, they're talking about moderation, so we're impacting that path. We're expecting different paths for different levels versus we're expecting this path to go away. So if we say the callous unemotional traits are moderator, then we're saying the relationship between video game playing and aggression changes based on the level of callous traits. Yeah. And that's just like interactions in ANOVA, where we're saying that each combination matters. So one across or down have different effects. So this is a scatter plot of a very simplified version of it. So if we were to take this and make this a t-test, or an ANOVA interaction, right? We could look at hours playing video games, and we could look at people who are callous and not callous. So that should be comparing correlated correlations, right? So we could say that one group has a different correlation from another group. Sorry, independent correlations. And that wouldn't be too hard. Like one of them's flat and the other one's not. That's an oversimplification of what's probably really going on, which is doubly continuous data. So if there was no interaction, low traits to high traits would have the same correlation, aggression to video game, or video games to aggression. So it doesn't matter what level of callousness you are, you get the same correlation between those 2 variables. You do get interaction. I just love this picture because it's kind of like twisty fun. Essentially what that's saying is that at different levels of callousness, the correlations are different. The trick here is that we're not actually going to categorize people. We're going to move them around. So what people want to do in this analysis is they want to group people into low, average, and high. It's very tempting because that's the way people report it, but that's not actually what's happening. What we're going to do is sort of pretend people are low, average, and high. So this is the other picture of it. This kind of gives you the more math version of what's happening. So we're going to say that each person is predicted by some intercept. Remember, B0 is the intercept. Gaming plus callousness plus their interaction. So we're going to tell it R to add the interaction. And then simple slopes, which is a simple effects analysis, is how we'll figure out what's going on in the interaction. Before we do that, though, we have to fix the problem that we're creating by adding the interaction. So the interaction centering has 2 problems, solves 2 problems. I love to ask this question. I put a big star here. This is one of my favorite moderation test questions. What is the purpose of centering? Usually what I ask. So we always talk about additivity. Right? So each predictor should add something to the equation, which means that they can't be perfectly correlated. So we check the correlations and we move on. By adding the interaction is actually pretty much perfectly correlated with A and B because it's comprised of A and B, or X1 and X2. So what we have to do is sort of fix that problem so it solves a multicollinearity issue. we couldn't add them together because adding them is a perfect transform. Multiplying is not necessarily a perfect correlation, but it causes multicollinearity problems, so it will solve that problem. It also makes interpretation much easier. So centering really is like, we're just going to subtract the mean. So essentially we're going to take everybody and move them to where the middle is 0. And that makes things much easier to interpret. So the easiest way to center variables is to take each person's score minus the mean for that column. So I'm going to take gaming minus the mean for gaming, callus minus the mean for callus. You can also do z-scores. Z-scores makes those b values beta. That makes it harder to interpret. So from the video last week, we talked about beta is easier to compare between two values, but harder to like understand what the heck is going on. But getting at this, what does this do question? So it's got aggression here. It is predicted by the intercept plus B for game plus B for what? Aggression and callus plus the interaction. Okay, times B. Once I center them, that means that when this score is 0, so let's say let's go with callus. When callus is 0, that means that it's at the mean. So the average score of callus, as we put in a 0 because we've centered them, that means that this marker's down. This thing and this thing completely drop out of the equation. So at an average level of callousness, the only thing we're left with is the average level of gaming's relationship to aggression. And I could go the other way too, but we're going to split on callousness. So when callus is average, I can now tell you the game to aggression correlation. Okay. Or the slope. So it'll be at average callousness. That's what it means when I say that the interpretation gets a little easier. Because when x is 0, that's now the average level of callousness. And that makes sense. So at average callus traits, game predicts aggression 1.2 points or whatever it is. So you'll pretty much always see people talk about centering. They don't always tell you which one they're doing. So if you're describing one of these, talk about mean centering. Because z-score centering, it has the same interpretation at average level of callousness now, but now B is standardized as beta instead of being coefficient B. And that's what this slide says. So it's the effect of the predictor at a mean value for your sample, and it's the average effect of that predictor across. So it's at this average level, it's games to aggression. Got it. All right, so just like ANOVA, if our interaction is significant, we're just kind of, the main effects of their thing, here's some numbers, but I'm going to really just interpret the interaction. So when I do a lot of these, I don't know why, I hate my life sometimes because we did a 5-way interaction one time and that was a dumb idea. But we're just mainly just like, the main effects are in a table if you want to look at them. Because really it's more interesting of what's happening with that interaction, so let's break it down. So if that interaction is significant, we're going to call this simple slopes. Before we were doing simple effects. They're actually the same thing. But simple slopes implies that we're working with slopes now instead of simple post hocs. But if my variables are dichotomous, then you just separate them into different analyses. So if callus was actually not callus and callus, one, don't center that, because it's one or the other. But then I just would break this equation in half. I would do this equation for just callus and just equation for just non-callus. So this makes it a little easier. And then at that point, you're comparing correlations between groups. If you have two continuous variables, this is where it gets tricky. So what we did before is we took one of the ANOVA variables and split it up, right? And then ran the other one. Same idea. This is where you're just going to have to trust me if you don't get it. This is the trust part. Okay. We're going to create low, average. We already have our average group. Okay. So the average group is the main equation. So we're really going to create these low and high. And these create in quotes because we're not actually going to categorize people. So I'm not going to break this into 3 different regressions, as in, like, I'm not going to take you are going to be low and only low, and you are going to be average. So we're not taking the data and, like, busting it up into 3 groups. Okay. Instead, what we're going to do is, I always think about this as like a submarine periscope example. We're going to move the data around and look at the middle each time. Okay. Move back and draw this. So our original scale, let's say, ran, I don't know, 1 to 7. And 4 was right in the middle. I'm making this up. I don't remember what it actually is. Well, to get those average people, I just subtracted the mean from everybody. So an average slip, all we've done is we've taken everybody and we shifted them to 0. So we just like picked this distribution up and moved it to 0. We can do that exact same thing to get our low and our high groups. Okay, so this would be what the participant score is in the data set. So before they had a 4, now they have a 0. But they're still on average and they're still in the middle. Okay, that's the important part. We haven't actually changed the shape of the distribution or the relationship of the points to each other. We've just picked them all up and moved them over. To get the low group, we're going to do the same thing but move everybody towards the middle. Okay, if you're in the low group, which way is towards the middle? Don't say anything you know. That would be cheating. Hopefully you remember. Wait, you as well. Did you do this?
I don't know if I did this one, because I remember you let us pick which ones. I can't remember.
Okay, if you're on the low group, which way is the middle? This shouldn't be a hard question, actually. Up. I know you guys are like, this is a trick question. We're going to take those low people, and we're considering those people who are 1 standard deviation below the mean. But to move them to the middle, we have to move them up. So we're going to shift everybody 1 standard deviation up. So let's pretend our standard deviation is 1 because math is hard for me. Right. This is where people's like, why, what? That's why you have to think about where am I moving people around. I'm looking here. This is the part my regression equation shows me. So where I'm getting the coefficient numbers. So I have to move the data set around so I can see it in this slot. The high people we're going to bring them down 1 from the middle. 4 from the middle, 2. So we're going to bring them down to the rest of us. The interpretation is exactly the way you would think. Low people are people who are 1 standard deviation below callus. So an average level callus, 1 standard deviation below average. For high is for people who are 1 standard deviation above average. But let's say we have this magic submarine periscope. We can only see them if we move them towards the middle. So for low people, we have to add a standard deviation. For high people, we have to subtract a standard deviation. And that's the trust part. And the only reason we do that is so that we can see the right slope. And so these numbers here would be just what the score in the data set looks like. So for this person, they went from a 4. On average, they're the average, so they're a 0. But if we pretended they were a low person, they would actually be a little bit above the low group. So 1. we pretended they were a high person, well, they're average, so we have to move them down a standard deviation to represent the fact that they aren't actually in the high group. So that's why I said I think about this as a periscope. I can only see here. So I subtract everybody and get the middle. And the low people, I shift them up. High people, I shift them down. So somewhere on the world of the internet, there's a really funny video of me talking about this from an example of people who are high and low status. And I was talking about the slopes, and I said, oh, so the high group, they don't care because they're high. Wish I could remember where that is. But the idea is like we're shifting people around to see them as if they were average. All right, so we're going to use this example from the Andy field. You do have to pick a variable to be low, average, and high. So we've got to pick one of these to shift around and examine the other ones. So back to ANOVA. We picked one, then we split, and then we looked at the other variable. Same idea. We're picking one to split. We're going to examine the other one. Okay. So if you're doing this and you're like, my B values aren't changing, you're looking at the wrong variable. All right. So let me load that data set. This is where we normally do data screening. So this particular example has an ID that we're going to drop, and then we've got compression, video games, and callous unemotional traits. So we're going to center X and M, so people still call this M, for the one you're going to do simple slopes on. Don't center the DV. We're not moving aggression around. All right, so what happens, remember the scale function from 1.5 zillion years ago, talking about z-scores, but we're going to turn scale equals false. So that's going to not make it a z-score, it's just going to subtract the mean. So it's a quick way to do mean centering. If you did scale equals true or you left it out, it would do z-scoring. There's nothing wrong with z-scoring, it's just most people like you to do raw coefficients, so using b and not beta. Yeah, I've done it both ways, but I think regular B works better. So if I looked at my summary again, so it does this sort of weird, what just happened? Oh, a summary of the letter A. Let's try again. Because I've imported this from SPSS, it does this weird like .v1. That is a lie. That's not the name of the column. I don't know what it's doing, but it's still called, it's just called zvid. So if you're like looking, or if you like to look at it up here, you'll see that it doesn't have that. So I don't know what that's about, but just FYI. I can see that the mean here is 0. So it's stuck both people where their average score is now 0 instead of 22 hours a week. Oh boy. And their callous unemotional traits at 18. 22. I'm trying to imagine 22 hours a week.
Someone did 38.
Yeah, that's a lot of video gaming.
Good job.
Maybe they're a Twitch streamer.
They're like, I don't know, farming and WoW, who knows? All right, we did this slide. Okay. We're going to run that model. Okay, be sure you use your z-scores because you created them. Why? Otherwise, you're not using them. Okay. And you don't have to make the interaction. So unless you use the process plugin, also does this as well. But if you were doing this by hand, in SPSS, you'd have to actually create this interaction column. We don't have to do that in R, so that's nice. Okay. So we're just going to Z1 times Z2. Okay. You don't have to put them in any particular order. I think I kind of forced them in a specific order for graph creation here in a minute, so you probably want to do X times M, is I think how I set it up. Okay. But using that little star creates that interaction for you. So when we run that, we look at a summary. This is what we'll see. Okay. So overall, that model is significant. So I'm going to look down here. I'm going to treat this more like multiple linear regression. So the model is significant, blah, 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 R squared. It's a pretty big effect. But what I'm really interested in is that interaction is significant. Okay. Now interpreting this B is not useful. Okay. So the slope, when you multiply these two variables together, is 0.03. Like, I don't know what that means either. Right, so when I multiply your video gaming time times your cows traits, your regression goes up 0.03. Like, meh, it's not easy to interpret. So instead, we're going to do simple slopes. Okay. All right. People use low as 1 standard deviation below, and 1 as high, or high as standard deviation 1 above. Right, we've already talked about creating those as backwards. You can actually do, some people do 1 and 2 standard deviations below and above. You can do any type of cut points. So you could do 5 points if you wanted. We're going to do what people traditionally do. All right, so our low group is created by adding that standard deviation. Our high group is created by subtracting that standard deviation. Here's my periscope example. So we are bringing them to the middle. So for low people, we have to pretend like they're higher than normal. For high people, we've got to pretend like they're lower than normal. And then I'm going to rerun those exact same models with low and high. And what you do with that is you look at the other variable. So if you're running this analysis and your simple slopes don't change, you're looking at the wrong variable. Okay. And hopefully x and x by m, I'm sorry, not x, m and m by x don't change at all. So the coefficients for the other variables should stay the same because you're not actually changing the data set, we're just pushing it up and down. So we're changing the relationship between m and, so callus here, and regression. We're just kind of like, whoop, whoop, moving it around. Okay. All right, stuck them all on here together, but let's look at running that. Right. So create my low and high. So for callus low, I took the z-scored column, so use the z-scored column, plus a standard deviation of the z-scored column. It's not z. I probably shouldn't have called it z. Old habits die hard. The mean-centered column. Right. And we're going to move them up. And then for high groups, I'm going to move them down. So if you're cutting and pasting, which I do as well, make sure they're 1 plus, 1 minus. Now if I look at my data set, I can see that I've got my original column, which is 0 and 0. The standard deviation is 9.6 points. So for my low group, they moved up 9 points. My high group, they moved down 9 points. And you wouldn't think this would work, right? We're just like kind of moving them around. But it does show you the correlation in different sections. So what's really happening is it's essentially zooming in on the correlation on the low end and zooming in on the correlation on the high end. But does not force you to dichotomize groups because that is a bad thing. You shouldn't do it. All right, I'm going to run those models. So here what I did for mod model low and mod model high. Took that original regression and added low and high. So you notice I wrote a note here. Be sure to do x times m. And then I always try to do this. Now we've already run this average model. So you're not rerunning the model. I just always try to put all three slopes together so that I'm not like, wait, where was the average again? Oh, it was up here. So just kind of keeping them together. And that is what's on this slide. All right, so for low callousness, for our low group, what we see is that the video games and regression are not related. Okay. And if they were, it would be negative. So we've got video game playing, aggression. At low callousness, this is a very slight negative slope. Okay. That's not significant. Okay. At average levels of callousness, it's positive and significant. So I'm going to try to make the lines different here. And then at high levels of callousness, the slope increases even more. So if there's moderation, so if there's a significant effect of the interaction, you're going to get a fan in some form. the slopes will make this sort of fan effect. If they're perfectly parallel, there's no interaction, just like those ANOVA pictures that we looked at on the test. So they will fan in some form. Okay, or they'll make an X. But you'll get some sort of crossing. Usually it kind of looks like this, or some version of fan where maybe they're all positive, but they're different strengths. So we did one of these looking at supplemental instruction, so our PASS program, and the GPA of the person going, and looked at how much impact each level of student got. So lower level students, did they get more impact than higher level students? That kind of thing. Now, the important thing to notice here is the intercept is changing for each one of these. That makes sense because we're moving the data around. But the interaction terms and the variable we're splitting aren't. So it's 0.76 the whole time and 0.03. So that's one way to check and make sure you're doing something right. So only one of these numbers should be changing. So that's why I said if it's not changing, you're doing something wrong, you're looking at the wrong variable. So if you report, split and report the same variable. So here's my interpretation. So at low levels of callousness, video game doesn't predict. At average levels, it predicts increasing regression, and at high levels, it's even more. The strength of the relationship is the strongest. And so that's the interaction, is that, on the low end of callous, this doesn't matter, but on the high end of callous, it does matter. And so we were able to do interactions now with 2 continuous variables instead of 2 categorical variables. And at this point now, you can mix and match. So that's one reason why I like regression. Regression and ANOVA are the same thing, and I have more options. So I don't have to use only categorical variables. I can now use a mix of both. All right, and this is just a picture, so we're going to make a picture of this effect. So a significant interaction will make a fan effect that either gets stronger to weaker or stronger to stronger. Essentially, you'll get slopes that come together or cross. Okay. And what we found is that increasing levels of callousness predicts increasing levels of video games' effect on aggression. All right, and we can do this in ggplot. Okay, but we have to do something new. I just learned how to do this, so you guys get the benefit of me learning geom AB line. We're going to manually draw those lines on. Okay. So we're going to create a scatter plot and then add some lines to it. So this is where we're going, and you'll see it kind of matches my picture. So I've got, this is the one standard deviation below, so the low group, the average group, and then the high group, and we're creating that fan. I have to kind of figure out, do I want to interpret it this way because the dots are everywhere, right? You can also add confidence intervals to this, but it got like really crazy, so I stuck with this, just drawing the lines on there. Okay. So let's see how to do that. Okay. So we've got our normal ggplot plus cleanup code. Here we go. So for the graph, we're going to do the name of the data set. This one is the non-switching variable. So this one's X, okay, and this one's Y. You'll see that M is nowhere in here. This should all look the same. This basically makes our scatter plot. Let me run this. Our ugly scatter plot with the dots are gray and the lines are gray. And then so I was saying right here, this part assumes that you kept the model names the same and you did X times M. If you did it wrong, just flip the variables and rerun the models. Because what happens is geom AB line works by you tell it what the intercept should be and you tell it what the slope should be. Okay. So this is what we did earlier for our mediation example. So part 1 is always the intercept. Part 2 is the slope. And if you run this and you get 3 of the exact same line, you just get 1 line, you use the wrong one. And you flip the order of them. And so what it does is it draws 3 lines. So I've got 3 AB lines. Look. I've got them in order. Model low, model average, model high. And then I just named the lines. So the reason that you name the lines is so that you get different line types. So they're not all just regular straight lines. So it looks crazy, but all you'll have to do if you keep your stuff in order is change the labels. So change this Cal here from Cal's emotional traits to whatever the example is. Okay. Be sure you change it in both places, up here and down here. So I'll show you all that. Hopefully it'll make the same graph I had. There we go. So what that allows me to do is I made a scatter plot. We've made scatter plots all year, and then I just told it, draw these lines manually on here. Okay. That is the easiest way. Now there are a couple of packages that will do mediation and moderation for you. They don't do bootstrapping, so that's one reason that we didn't use it. And then the simple slopes one doesn't allow you to, it doesn't really tell you what's going on in the background. I would rather you understand, like, to create a low group, I have to add a standard deviation. To create a high group, I have to subtract a standard deviation, because then if you have a three-way interaction, what you do is you take apart one of them and look at the two-way effects, and then break apart the other one and look at the one-way effects. All right, if you can avoid the three-way action, do it. But like next semester when Mitchell asks you about three-way interactions, okay, now you understand, like, we're breaking them down one piece at a time. Okay. So while I know there are little packages that can do this, I want you guys to do it the slightly longer way because I feel like it helps you understand how we're making those slopes. Right, so before in ANOVA, we took each group and like broke it down. Now we're making these slopes by manually moving people up and down. All right. So then